I want to thank the organizers for this kind invitation and to play piano and to talk about logic. And we're at the second phase now. So this is about aspects of Gödel's incompleteness. And I'm going to discuss various forms of G1 organized into thematic groups. The various relevant notions of adequacy are compared. I discuss various forms of G2, which are formulated in terms of interpretations, starting with the well-known PA is not interpretable in any theorem of PA, including thematic characterizations of the formal consistency statement up to provable equivalence. And I present a somewhat novel proof of G2, slightly novel based on the notion of explicitly remarkable set, which cleanly separates the auxiliary construction from the direct verification. In other words, once you have this explicitly remarkable set, the rest of it has no diagonal. The rest of it has no is totally normal kind of verification. So the only sort of queasy thing one has going on is the notion of remarkable set, which is then sort of refined to make it look very innocent. I'll say at the end what I expect to get out of this, since this is the so-called, this is the 85th so-called slightly new proof of Gödel's second theorem in existence, where the number 85 could be changed to 373 if you like. In other words, there's a lot of proofs of Gödel's second theorem out there. All right, so and then I want to talk a little bit about what tangible incompleteness now looks to me like at the higher large cardinal levels. I want to say a word about what's going on there and where I'm at with that. All right, so let's start with Gödel's first incompleteness theorem. Now, not everything I say in all my talks is new, you know. It can be old hat or other people's stuff and so forth. So I will caution you that you don't have to fasten your seatbelt all the time here. Okay, so actually I found this wonderful article, Finding the Limit of Incompleteness, by the organizer of the meeting, the chief organizer, in the Bulletin of Symbolic Logic, 2020. And there's a lot of nice material in there and a nice point of view. And I sort of came to a lot of the some of the same kind of ways of looking at things. So there's a fair amount of overlap between what I'm going to say and there. But I really do want to indicate some lines of investigation that I don't think have been completely mined out at all. I think this might be the main purpose of this first section is not anything terribly new, but maybe a slightly new perspective on what kind of additional research one might do on G1. Now, okay, by a theory, I'll always mean first order predicate calculus with equality, although the issue of whether you should have equality or not is something, you know, that can be addressed. But, and a theory comes with a designated language of constant, relation, and function symbols. And it could be infinitely many or uncountably many symbols is okay. Now, the most common way to formulate G1 is to assert that any theory T with an adequacy condition has a wildness property. Okay, that's the general framework I'm talking about. Any theory with an adequacy condition, in other words, any theory that's pretty good is pretty bad. That's what Gödel's first theorem says. And there's several important kinds of adequacy conditions and wildness properties. So common adequacy condition on a theory T, and I give multiple choices here, that it's consistent is almost always going to be needed, sometimes not, but often you have to say consistent. There might be setups where, in fact, if T is inconsistent, it's just fine, it's just trivial. We can have that too. But basically, for most of the time, we want to have that. Okay, so T is consistent as an adequacy condition, that T is either finally axiomatized or axiomatized by finally many axiom schemes, or recursively axiomatized, very commonly. These are also adequacy conditions that are very important. That T interprets a given theory K, and K might be finally axiomatized or axiomatized by finally many axiom schemes, or recursively axiomatized also. And by the way, often you might actually really write down a particular K, like Robinson's Q, for example. Or you merely might ask for some K of a certain kind that does something. No, this is a very general kind of G1. I'm supporting thousands of interesting G1s with this stuff, that are all slightly different. Okay. Another one is T is consistent with an interpretation of a given theory K. This is sort of like this, often sometimes called tolerance, in the same language as T. Finally, and the K might be finally axiomatized by finally many axiom schemes, recursively axiomatized. The language of T is or extends a given language. So there's all these forms of G1, that are, you often teach it this way, that it's going to be for arithmetic. The language is going to be fixed as the language of arithmetic, for example. You might have that. But I'm supporting in A through D, I'm supporting versions of G1 where you don't say anything about the language, anything at all. So the language of T is given, and that gives another realm of things, and also that T is actually literally proves, not interprets, literally proves a certain theory. So, might have a formulation of G1 which says any system that contains Q in the language of arithmetic, this kind of thing. All right. And common wildness properties of a theory, just being incomplete. That's kind of the purest thing. Just being incomplete in its own language, meaning that there's a sentence that's neither provable or refutable, is a wildness property. And essentially incomplete, no consistent extension by finally many sentences makes it complete. The set of theorems, there's a whole bunch of stuff about we all know about, you could say the set of theorems is complete RE or is not recursive or is not primitive recursive, whatever, things like this, or any finite extension or any recursive extension. So this is like essential undecidability is inside here, for example, and then the set of theorems and the set of refutables the set of provables and the set of refutables are recursively inseparable. Is another kind of thing. And then, assuming the language of T is or extends some given language, you can look at all of A through D and restrict it to sentences of a given sublanguage. So for example, you can look at you can ask that the sigma 0, 1, you can conclude that the sigma 0, 1 sentences are neither, that there's incompleteness with a single quantifier sentences, things like that. Or the set of provable pi 0, 1 sentences is RE complete, is complete RE, and so forth. All that stuff is covered by this. So this is sort of like, these are the wildness properties and the adequacy conditions. All right, now obviously there's other interesting adequacy conditions and wildness properties that you might like that I haven't listed. That might well be the case, okay? And nobody has any problem with that. Now, the systematic investigation is the template for G1, which is let T obey a chosen one or more parts of the adequacy conditions, then T has a chosen one or more parts of the properties A through E, of the wildness properties. So you have an enormous flexibility in this. And we want to figure out which of these statements are true. Now, some of these statements are going to have free variables, capital K for theory, like in the adequacy conditions. We'll want to know if I have two different instances of the template, whether they're the same for all K, for example. And we all know that Robinson's Q is very good for certain things. We might want to know that whether those things are whether any K that works for one of these things works for another one of these things. If I have two different formulations of G1, is it the case that any K that works for one works for the other? All of this is included in this systematic investigation. See, I want to keep you people busy, right? Okay, so the most elemental. Now let's actually do a little bit some specifics and high points here. I mean, I'm obviously not going to be able to even come close to classifying and analyzing this template. So let me mention a couple of things. I think the most elemental form of G1, involving only the most rudimentary of notions, is arguably the following. I call it pure G1 finite. So there's a consistent finally axiomatized theory K, such that any consistent finally axiomatized theory interpreting K is incomplete. All right. Now, of course, this is kind of not terribly satisfying philosophically, because it doesn't say much about what K is. The idea, of course, of Gödel is that K should be something that everybody accepts as very basic, you know, like a little piece of arithmetic. And we now know that Q is very good for this, as well as other systems, any system that's mutually interpretable. All right, so Robinson's Q, yes, Robinson's Q is the most commonly used for pure G1, as well as its many natural variants. See, the thing about pure G1 is it doesn't mention recursivity. It doesn't mention interpretations. Excuse me, it is basically on interpretations, but it doesn't have recursivity notions, and it's only finally axiomatized, which means one sentence, if you like. All right, and it also doesn't, pure G1 also doesn't commit yourself to any particular system you love. Just says that there is one. All right, so Robinson's Q is the most commonly used for pure G1, as well as its many natural variants, in the sense of being mutually interpretable with Q. So obviously anything mutually interpretable with Q you can use. There's no, you can use anything that interprets Q, in fact, yeah. There's no known natural system K for pure G1 that does not interpret Q. All right, so here is an interesting challenge, which I believe has not been met but not been explained why it's not being met, which is there a natural system that doesn't interpret Q that's finally axiomatized, which you can use for pure G1, okay, or for many of the other versions of G1 here? Is there anything better than Q? Now there's the schematic form. There's a consistent theory K with finitely many axiom schemes, such that any consistent theory T axiomatized with finitely many axiom schemes interpreting K is incomplete. And here there is something natural better than Q, in that Q doesn't interpret it. It's called R, also due to Robinson, and I think you've probably seen this system. It's got infinitely many axioms, and it's interpretable in Q, but Q is not interpretable in R, and you can use this. But now R is very recursive. R is very nice. R is really kind of schematic, but it's not. R does not follow the usual criteria for being a system based on finitely many schemes, because the schemes are, they have to do with n bar, where n bar is the numeral for S, the formal numeral for n, S 0. And that's not an official scheme in the usual sense. So this should be cleaned up some. Maybe we should have a better definition of what we mean by schemes that would include R, official definition, or we should simply show that that you can change R around a little bit, and so it's really actually an axiom scheme, finitely many axiom schemes. I thought of this when I was preparing the talk, and I haven't thought this through very much, but you might want to do either approach. But basically, R is schematic. All right, so now again, let me emphasize what's missing is insight into the special status of Q and R, and there's some variants, I think, of R. I'm not sure exactly what's going on here. I know Albert is an expert in this. Those variants of R that are slightly weaker than R, than some version of R, are they all mutually interpretable? Unmute yourself. You're muted.
Here it is. Yeah, I think so. Yes. So all these variants that people found, where we can drop the linearity axiom, etc., are all mutually interpretable.
All right, so there's something fundamental here. There's something fundamental here that's going on. See, I think there's some missing theorem. I don't know quite. I have a proposal for a missing theorem, but it's not the one that we really want. The proposal that we really want is some criteria here that shows that Q and R cannot be improved on. Q for the finite axiomatization, R for the schematic thing, cannot be improved on up to interpretation. But I think that we know, Albert, in the case of Q, we can certainly artificially go below Q interpretable, right?
Yeah, well, it's trivial.
That general fact that you have to minimum.
Because you have the series of some false sigma sentence. So
right. In fact, I think you quoted me as playing around with that once, right?
Yeah.
But also with R, can you do that also with R? You're muted. Albert?
Here I am. Yeah, so I don't know. So it's not clear that you can. So of course these things are all extensions of R, right? The false sigma sentence series. But so I
So
don't.
it's not obvious to you that you can go below R in interpretability.
Oh, what? Yeah, no, that one is known. So recently, Fedor Pakhamov has shown that modulo interpretability, there's no smallest essentially undecidable theory, right? So you can go below R.
Below R, you can go below R and keep this G1.
Yes, precisely.
Okay.
But so the problem of Fedor's argument, at least as far as we understand it now, is that it doesn't give us an effective way to construct this series. So I don't quite know what the theory looks like.
So what do you mean, Albert? I mean, so basically for any for any undecidable RE degree, we have this essentially undecidable theory.
Oh, okay, yes. Okay, sorry. Fedor is right. I'm confused.
So these are recursively axiomatized.
So right, for every, okay, but this was already proved by Schoenfeld. So for every RE degree, you can find an essentially undecidable theory that is in this degree.
Now, what if you insist that everything be found in many axiom schemes? By law, that's all you want to look at. Then what happens?
Yeah, that's a good one. Am I confused here?
Well, I watched Fedor go like this, which means he doesn't.
I don't know. I mean, probably it's true that you basically that you could construct the theories to be axiomatized by finitely many schemes, but yeah, I mean, I don't know exact construction.
The problem is we only know for pair theory. So an RE pair theory always can be axiomatized by a scheme, but we don't have a general theorem of that form. So
all right, good. Look, as you know, I haven't really. I'm not making any claims here of anything new about G1. I'm just trying to stimulate conversation and research. It looks like I'm doing it okay by that now. So so far so good, right? Okay, so let's move on here. Now, as we vary the wildness properties we seek for T, how does that affect the choices of K that we can use in the adequacy conditions? So, you know, you might have essential undecidability, you might have incompleteness or undecidability but of degree R, 0 prime or whatever. How does that affect what Ks you can use that are finally axiomatized or axiomatized by finitely many schemes? So I think, Albert, that's probably not been looked at much. Am I right or wrong?
Sorry, Harvey, I was just a way to check whether I had an axiomatization of R that was a scheme. Can you repeat the question?
Okay, I'm sorry. If I change the wildness property from incompleteness to undecidability to essential undecidability to whatever,
right?
How does that affect what Ks I can use?
Yeah, okay, so I don't quite, so we discussed this and then I looked into it. I think I only think but I don't quite remember the answer. I think only for the weak cases, it's not clear, right? So as soon as you have RE, etc., I think that it would coincide. But if you have finite, for example, if I remember it correctly, we were not clear whether it coincided or not.
For finally, actually, like Q. Yeah. Okay.
Yeah.
All right. Good. I'm glad to hear that is something neat to think about. There could be some pretty interesting things there, particularly when you, yeah. All right, so let's see. Now, here is a little different twist in this. There's also an attractive simplicity investigation. There's some reasonable natural measures of the complexity of presentations of finely axiomatized systems. You can count the number of occurrences of symbols other than parentheses and commas. Each occurrence of a variable counted as one. And we can, and you can, and where you also count, you count each occurrence of a connective and a quantifier and so forth. You can play with this, but there's a reasonable measure or measures. We seek information on the smallest complexity of a case supporting pure G1 or other instances of the G1 template. So using a Q is a pretty big number, because Q is kind of a big thing. But you know, there's a much better system for this purpose called Adjunctive Set Theory. And I assume most of you know this. AS, Adjunctive Set, I think AS abbreviation I saw, right? AS, you know, where you X union singleton Y and what is it, that there's an empty set, some the variants like that. These are all also mutually interpretable with Q, and the number of symbols is rather low. So here's a conjecture. Any finitely axiomatized system K usable for pure G1 and variants of G1, any ones you pick, of complexity at most that of AS, which is a pretty low complexity, by the way, whose complexity is at most that of AS, is mutually interpretable with AS. Maybe I should say interprets AS. Probably it's safer to say interprets AS, not mutually interpretable with AS. Yeah, I should say interprets AS. Okay, now that sounds like the kind of conjecture that is possibly within reach, probably with the help of a computer. And which, in order to solve, you have to do some interesting computer work, plus you're going to have to do some serious logic on top of that. So if you can do that, it should lead to some other things, understanding of G1. So that's my proposal for a conjecture, hard-nosed conjecture. Okay, the most, which I think is promising. The most common languages used to formulate versions of G1 are arithmetic, with and without exponentiation, with and without printed recursive function symbols, with and without less than. Set theory with membership like adjunction, set theory with membership, string theory under concatenation. These are standard languages when you want to be specific, when you want to have specific languages with G1 with specific languages. Now, there's some important special classes of formulas that people worry about, like pi 01, sigma 01, and sigma 01 using polynomial equations, so-called Diophantine statements. And this is asking for a common zero defining many polynomials with integer coefficients. So this is where G1 meets Hilbert's 10th problem. And for example, there's some really interesting work by Emil Jerebek with the title. That's why I couldn't remember what this was. I'm looking at Jerebek's bibliography, right? I surely can spot the paper that has this topic, and my eyes glazed over division by zero, but that's what it's called, and it's about the provability of deciding whether Diophantine equations are provable in the system Q, right, Albert?
Yes.
and division by zero, I haven't yet. You probably know why it's called that, right? But anyways, there's probably a lot of division by zero going on that has to be avoided. So that's my speech about G1, and have a lot of fun with G1. Now let me talk about G2. I actually did a lot of work on I did a lot of meandering in various directions about G2 over the years in the FO email list for 14 years or 15 years, 2003 to 2017. And I just sort of recently collected my thoughts about this for this talk. I just want to prove to you that I have been thinking about this and actually wrote down some stuff. So here are the posting numbers once of my file, which is now up to 800 and something. 165, 166, 167, 168. I want to prove to you I've been busy with this topic. 174, 284, 285, 286, 305, 306, 307, 343, 344, 346, 37. Oh, and one of them that I didn't number, explaining some Gödel. And then I calmed down a little bit later and ended this business with these three. And these have a lot of proofs of a lot of the claims, but they don't have proofs of all the claims, and it's fairly detailed. These are model theoretic forms of G2. By model theoretic, I mean basically they rely on the notion of interpretation. There's only the only real notion in these formulations of G2 is the notion of interpretation, and with most of the proofs given in detail. And I had most of these ideas from 2003 to 2015 or something in here. All right. So then and that's what I want to talk about here more seriously. Then I got into a different mood. And these are 5 different versions, each slightly different than the other, of how to prove Gödel's second theorem using this remarkable set construction, which is a very pretty idea, which is not very novel, but slightly novel. I'll call it slightly novel. So that's what this later stuff, most recent stuff is. So as I said here. Okay, now I want to talk about this model theoretic G2. And now I should make it clear, I'm talking about model theoretic statements of G2, not model theoretic proofs of G2, just model theoretic statements of G2. Actually, I'm not even sure how I would classify the what's model theoretic proofs of G2 really mean even, but basically I'm talking about just pure statements. We're not talking about proofs here. All right, so let me just pass through just to show you that I was doing this kind of thing back then. I copied little excerpts from these papers in 2016, these 3 papers in 2016. And the basic philosophy was that I didn't like the way that Gödel's second theorem there's something really unusual about the way Gödel's second theorem is usually stated that isn't true of other great mathematical theorems. Namely, it refers to an object that nobody wants to look at and nobody wants to form. That's not true of the fundamental theorem of calculus or FLT. I mean, it's like saying for FLT, I don't really want to look at an exponential of 2 numbers, like 7 to the 8th or something. I just don't want to look at that such a thing. Or something like in calculus, like I don't want to look at an integral of a function. I mean, the point is nobody wants to write down and look at the consistency statement. And your consistency statement is not going to be the same as mine. It's going to differ in some trivial way. And by the way, your consistency statement and my consistency statement, if we're just doing normal work are going to be actually wrong. They're not even going to be correct. So this is a very unusual situation compared to other great triple great theorems of mathematics. So I was kind of interested in that situation very much. I'm not the only one. A lot of people have been interested in this point of view. That it would be nice to have a few things surrounding this that would clarify the situation in several directions, by the way. But here are some. So I kept finding that it was very natural with this approach I was taking. The natural approach is that what Gödel's second theorem is really saying is that you can't interpret things nicely. You can't interpret things nicely. And the consistency statement allows you, by Gödel's completeness theorem, to interpret things very nicely. So how can consistency be provable? Because then you'll be able to interpret things nicely. So you'll see what I mean by that. So I found that this naturally works a little different. And then I'm beginning to understand it more uniformly, but I haven't really worked it out properly. But if it's PA based, it turns out to be very easy, much easier. If it's PRA based, there's a little more thought. If it's based on a finitely axiomatized system like CIFA, that's not strong. What do I call it? Strong exponentiation, iterated exponentiation. All right, iterated exponential function arithmetic. I forget what the S stands for. Anyway, so okay, that's with iterated exponentiation instead of a normal exponentiation. I talked about an EFA based one. I'm not sure that I'm endorsing that right now. I have to look at that more carefully. But anyways, you don't, with these interpretation forms of Gödel's second theorem, you don't have to assume the system is effectively presented. But if you want to do it with the usual way, usually using Kahn, obviously you need to know the system is recursively presented. Otherwise, what does Kahn mean? Or effectively presented in some way. Otherwise, what do you mean by the Kahn statement? So this liberates that from that. Is another point in this. All right, so as you can see, I looked at this for these systems. I didn't actually formulate it properly for higher systems, but it should be done more or less straightforwardly. I stated it for strings and also sets. And with sets, it's very interesting. One has to come up with the right form of bounded set theory that really is appropriate here to lay the groundwork and infrastructure. There's some interesting things here. And then I got interested back then, already even well before that, all the way back to 2003, about how to characterize consistency statements. So these are excerpts from these articles in 2016 in the FOM email list. But I decided that there's something I don't like about this way of doing it, because this is from there. Whoops, I'm sorry, I went too far. There's something I don't like about doing this, and I put it in capitals, and you'll see what I mean. Just a second. Here we are, capitals. These no interpretation forms of the second theorem I formulated the entire statement of G2 in terms of interpretations. Everything was interpretations, and that can be confusing to read. So recently, I just restored some proper balance here for immediate understanding, and the current formulations are much easier to read, and are much easier to read than these older ones that go way back. They're easier to read. And you can get the older ones trivially by jazzing it up with interpretations. So that's not a problem. All right, so let's talk about something specific. No consistent extension of PA in the language of PA is interpretable in any theorem of itself. No consistent extension can be interpreted. No consistent extension of PA in the language of PA can be interpreted in itself. Okay, this is a very neat statement. It's not hard to prove. I'm going to prove it here, and I'm also going to explain to you why on earth I would call this Gödel's theorem, Gödel's second theorem. Right? I have to explain to you why I would even call it Gödel's second theorem, but it is. You'll see what I mean. In other words, what I mean is you can trivially use this theorem to derive the usual Gödel's second incompleteness theorem for extensions of PA without doing any serious work. That's what I'm saying. Okay. The second version is no consistent extension of PRA in the language of PRA is interpretable in any pi01 theorem of T. And we'll see that if I don't put pi01 in there, this is false. Okay, this is false. All right, now, and finally, when we get into finally axiomatized realms, and low down even, CIFA, super exponentiation. I know what I call that. S stands for super exponential function arithmetic. Sorry. Okay, no consistent extension T of CIFA. I meant in the language of CIFA. Is interpretable in any pi01 theorem of T. That's false. In any pi01 theorem of T that only uses zero successor plus times an exponentiation. You have to restrict the language of the pi01 sense. Now, I know you're used to not restricting the language of pi01 senses, but that's because you're happy with induction or something or another. And that's what we just don't have here. So this is important. All right, first of all, why are these Gödel's theorem? Why is this Gödel's theorem? All right, number one, suppose T is an RE extension of PA in the language of PA that proves con T. We want to show that T is inconsistent, right? Then con T and infrastructure. I mean, you can't just use con T, it's just sitting there without any infrastructure. Con T and infrastructure is a theorem of T that interprets T, where infrastructure is the infrastructure needed for the Gödel completeness theorem, is readily provable in PA. The infrastructure is readily provable in PA. So I can look at con T and infra. Thus, theorem 2.1 is violated. Okay? Because PA supports Gödel's completeness theorem by taking genuine infinite paths through a tree that's trying to build a model, a la Girdle, by arithmetic formula. So instead of me pounding your head with this, these notes will be made available quickly. You can think about it yourself. It's very pretty. There's no problem whatsoever in deriving the classic Gödel second theorem for extensions of PA in the language of PA this way from theorem 2.1. And the mode of proof is the Girdle completeness theorem. See, I like the way that I like the synergy between Gödel's completeness theorem and his second incompleteness theorem. It's kind of fascinating, the synergy between the two. All right, now the second one, suppose T is an RE extension of PRA that proves con T, then con T and infrastructure is a pi01 theorem of T that interprets T. And you want to do the same argument, but not so fast, because PRA doesn't really support GC all that well, because PRA doesn't have any serious induction. It's only got induction with respect to bounded formulas, right? So you got to be a little bit careful. But you have the controlled branching tree. We know how many nodes at any stage, just an exponential. We can to get a complete diagram and extending T. Okay, so PRA attempts to do the leftmost path, but maybe it fails because it can't get past a finite place. But that's also a cut that can be used for interpretation. This method of cut, this method of cuts to build models is what's used here. All right, so this works, and I can't remember exactly where. I'm sorry that I'm a little bit unprepared here for a second. You very badly need that this is pi01 in order to pull this off. Okay, I'm sorry I can't locate the exact spot, but you very much need that this is a pi01 thing to pull this off.
Harvey, do you mean over a base theory like Q?
No. The point of this is that there's no base there.
It's really just a pi1 sentence. So you don't have any.
Right. It's just formal.
But you don't have anything like the.
No, because that's added to the infrastructure. Yes, that's added to the infrastructure. See, that's another nice thing about this. This whole nuisance base theory nonsense is completely gone. All right. Now with CIFA, it's more delicate. But it has to be pi01, 0 successor plus times exponentiation less than. In other words, obviously, if I had the full language here, I could obviously interpret it because you can interpret it in itself. And it is a pi01 theory in that sense. But the point is, you're asking that it not be, you're saying it's not interpretable if you tie your hand behind your back and only allow exponentiation without super exponentiation. That's what I'm saying. And you can use this to derive Gödel's theorem again. Now, actually, you could actually formulate con in this form also. But anyways, so this is also states Gödel's theorem. And now let's see. Now let's prove these facts. Okay, that's how you get Gödel's theorem from these things without doing any real work. I mean, you have to do some work. There's no question about it. I'm exaggerating, but you don't have gory work with your hands filthy in consistency statements, right? Okay, so let's see. How do I prove that no consistent extension of PA in the language of PA is interpretable in any theorem of T? Well, let T extend PA in L of PA and be interpretable in phi and phi provable in T. Now, PA proves phi implies con phi by soundness. See, you have all the induction because you were extending PA. Also, con phi implies con T because we know the relative consistency of interpretations, right? In other words, con phi implies con T is provable in PA. Hence, T proves con T by transitivity. And that contradicts G2. So in other words, I'm actually proving these new forms of G2 using G2. And then I'm deriving G2 from these things. Okay, all right. So there's okay. Now I didn't actually go through all these, but well, I guess I did this one. You can do this one too, but this one here, but you really do need that it's pi01. And in the argument, you definitely need, since we don't have much induction in here, we can't use, the soundness argument doesn't work. Unless it's pi01, then the soundness argument will work. I think at some point you need help from cut elimination, which is easily available in PRA. So, and by the way, this is false. Look at this. This is false if I didn't say pi01, because PRA plus the Ackermann function is total is pi02, right? And that's interpretable in Ackermann is total plus infrastructure. Okay, so clearly I need to know this is pi01. Okay, and so you can do this, and I think you have to be careful a little bit with cut elimination and other machinations. Should be all right. I didn't have time to actually write this out for, I think, even weaker systems if you're careful, but there's some traps in here, because once cut elimination is not available, you have to be more careful with things. So I didn't really get into this. I will when I put up the final notes for the talk. I'll suck this more dry than it is. All right, so model theoretic characterizations of the Kant statement immediately fall out of this development. And I also knew this some time ago. So for RE presented extensions T of PA, Kant T is the weakest sentence. Kant T is the weakest sentence over PA in terms of probability, is the weakest sentence over PA that interprets T. So if you want to, I mean, we know that Kant T interprets T, but it's actually the weakest thing that does. And you can prove that. Here is how you can do that. Oh, I said it was the weakest one. Okay, I'm confused here. Is it the weakest pi01 or is it the weakest one? I'm sorry. I'll clean this up. I'll clean this up after the talk. I can't remember whether I really need pi01 in here or not. Let's see. Suppose phi was arbitrary and interpreted T, then Kant phi implies Kant T is provable in PA. That doesn't use phi is pi01, does it? No.
No.
And that this is provable in PA. Again, doesn't use it. I think this is right. I think that this was right. I don't need that this is pi01. Does that seem right, Al? Probably, right? All right. Now for PRA, you definitely need it. For PRA, you definitely need this, and it will show up when you try to really do this. You see, because the soundness is awkward. Any kind of soundness is awkward if you don't have induction. You need to do, you need to know that you're dealing with pi01. All right, same thing here. All right, okay. So let's move on.
May I ask a question? May I interrupt for a second about the formulation of theorem 2.4 or 2.5? So interpretability over PA is equivalent to pi1 conservativity. Is that so, by Ori Hayek? So what you are claiming here is that Kant T is the weakest sentence which is pi1 conservative over any arbitrary t.
Probably so.
Which is rather strange because t may be
It's
t
an
itself
extension,
may be
T is an
pi1
extension of PRA.
We can clarify, but this I think needs to. There is something I don't quite get in this formulation of the theorem.
Yeah, Lev is right. I'm also not. We should think about this formulation.
Well, okay, if there's a mistake, here's what the fix is. You fix a fragment of, you have to fix a finite fragment of PRA and say it's weakest for the pi01 sentences in that fragment or something. That's probably what's going on. All right, let me look into this because I do want to finish the talk.
Yeah, one should be more careful here. Yes, indeed.
Yeah, but I know that the kind of fix I just mentioned is probably what's needed. All right, so, all right, in other words, this has to be more language dependent. All right, so now the idea of using the notion of remarkable set to push all the work in proving G2 that can be construed as diagonalization or mysterious into recursion theory is the idea. In other words, there's this little bit of a recursion theory that might be viewed as maybe mysterious, and then there's this just fun playground of logic which is fun and not mysterious. That's the idea. And then the part that looks recursion theoretic is beaten to death to look the most trivial possible. So that's basically what's going on here. And we might be able to get something new out of this. I don't know what yet, but it's possible. All right, so a set is remarkable if it's an RE set and it agrees somewhere with every RE set. Now that sounds pretty weird. It's an RE set which agrees somewhere with every RE set. The only way you could possibly have that is the complement. So you could actually see that this is equivalent to being not recursive, to being an RE set that's not recursive. If an RE set has this property that it agrees somewhere with every RE set, that just means that it's not itself not recursive. But this is the way I want to state it, that it agrees with somewhere with every RE set. Now this lends itself to an obvious strengthening. This lends itself to an obvious strengthening, and that is let's call it EFA remarkable. Another name for it is explicitly remarkable. It's EFA remarkable if for all RE sets B, there is an E such that EFA proves that A and B agree at E. In other words, you can find a place that it agrees with every RE set, but you can do more. You can actually point to an integer where they agree. Point to it and prove that it works. You can point to it and prove that it works. It's the most kind of obvious strengthening. Now that's a kind of subtle notion. That's a kind of an interesting notion. Now there is an EFA remarkable set. What you do is you take the set of E such that E is a member of WE, the Eth RE set. Take the set of all E such that E is a member of WE, and let B be WR, let B be an RE set. What's the particular number that they agree on? R, the index. The particular number that they agree on is R. All right. So the only hint of a diagonal argument so far is the definition. A equals the set of E, so that E is an E, WE. Now we can prove Gödel's second theorem. Sorry, that's called Gödel's second theorem. That's my old abbreviation. We can prove G2 starting with any EFA remarkable set A whatsoever. And the idea is this: we start with a remarkable set A, and we pick a B that's very closely related to A. We take the strong negative of A. That's an RE set. The strong negative of A is an RE set. And then we just go to town with that, with A and B having an explicit place at which they agree. All right, so let A, B, E, F, A remarkable. We're going to apply A to this set. And you follow your nose, do what you have to do in order to show that prove Gödel's second theorem. Okay, never mind the details. Talking about them is not going to do nobody any good. You can just do that as an exercise, or just look at it when you see it. Okay, so in other words, this is just a verification. I mean, it's glaringly using Hilbert Bernay's derivability conditions all over, reflection of approval, it's provable, and all that junk. All right. So we can look at it this way: we cannot apply any kind of remarkability to A and complement of A, because complement of A is not RE, right? A and not a complement of A don't agree anywhere. But we can do the next best thing to complement of A is the next best thing is the negative form of A over here. That's the next best thing. That's the next best thing to the complement of A. Or this here. That's right. Okay. And that's what we did. All right. There's some nice things about this. So for all of this effort to remove mysterious diagonalization from the proof of G2, it would be nice to get some good, solid, additional proof theoretic information. At this point, I don't have such a thing. But I've been finding out, now this you might be interested in, I've been finding out from both the category theorists and the type theorists that the category theory community and the type theory community both are quite wired into at least some forms of G1. They think they understand G1 for their subject, but they both have no clue as to the meaning of G2 for their subject. No clue. I talked to Kokan about this one, and I talked to this, I can't remember his name, this category theorist at Cooney Graduate Center.
Nosolinovsky, I guess.
That's right. I talked to him at some length about this. He doesn't know what G2 means in category theory. I mean, it's not like I asked him and he said, I don't know. He knew for a long time that he didn't know what G2 means in category theory. And Kokan says he has no idea what it means in type theory. So this proof I gave there, it seems like it doesn't seem to be as logic-y as normal. There's something about it that's this remarkable set construction or something. So I just asked them both to look at this proof and see if they came up with anything. Actually, I haven't heard anything from them, which is a bad sign, of course, but so be it. Okay, now let me finish the talk by telling you about something else, which is incompleteness out there in the wilderness, okay? Pretend you're a mathematician skeptical about incompleteness, okay? I'm going to now get you very excited. That's what I'm going to try to do. All right, every order invariant subset. Now, you and I know what order invariant means. It means it respects the equivalence relation of order equivalence and all that, Mathematicians know what this means in various guises and notions and so forth. And they like it because there's only finitely many of them. And if you fix n and k, and q means the rational, so this is the interval 0 to n. Okay, every order invariant subset has a maximal square. What's a square? A square is a set of the form B cross B, or E cross E, if you like. And no, S cross S. That's what in my papers. S cross S. So they all have a maximal square. This is Zorn's lemma or a particular construction. Actually, this is a nice undergraduate exercise. And furthermore, it can be done constructively. This is constructive, actually. You can get a maximal square. It's not a pretty sight. You don't know what it is because you do what's called a greedy argument, a greedy construction. But it is, in fact, effective. I should add, the point is it's effective. All right. Now, every order invariant subset has a maximal square, which is also order invariant. Isn't that wonderful? Well, it's totally false. It's quite easy to prove that this is completely false. The maximal squares are recursive, but they're not very nice in general. They're not very nice. All right, every order invariant subset has a maximal square, which is order invariant at least over the integers. Come on, at least order invariant over the integers. There's only finding many integers I'm talking about, right? From 0 to little n. So it almost sounds like Ramsey's theorem, maybe, but it isn't. It's actually close to the truth, but it's not quite true. Okay, and by the way, this is not easy to refute. This takes some work. So we already got the mathematician excited. He's going to have to do some homework right here. After this homework he can do pretty quickly. This one will take longer for him to do. All right, every order invariant set has a maximal square, which is order invariant over Z1n. Maybe the left endpoint is annoying. That's right. The left endpoint is annoying. If you get rid of the left endpoint, this is the theorem. It's a theorem of countable combinatorics. I'm stopping here for a second because I forgot whether this can be proved constructively. I just can't remember. I just can't remember whether I can prove this constructively or not. But I do kind of know, I'm not completely convinced that I have a proof, but I do kind of know that you need to know consistency of piano arithmetic to prove this. I mean, there's some logical strength in here. Okay, it's kind of interesting. All right, now let's get bolder. Let's get bolder. Every order invariant set has a maximal square whose less than 1 sections are order invariant over Z1n. The less than 1 sections, this is a standard construction in math. You fix any number, any of the coordinates, 0, 1, all of the coordinates, not all, you don't want to do all of them, but you fix some of the coordinates to be any rationals less than 1. Any rationals less than 1. You just plug them in, and then you get a lower dimensional set, right? And I want that lower dimensional set to be order invariant over Z1n. Now, obviously, this over here is a special case. If I were to take the trivial section, the section where I don't fix any coordinate at all. If I take a section where I don't fix any coordinate at all, then I'm back to over here, right? But now I want to actually fix some coordinates to be any rational. Then I get a lower dimensional set, and I want those to be order invariant over Z1n. The claim is that that statement is equivalent to the consistency of large cardinals. Okay, that is equivalent to the consistency of large cardinals. That's independent of ZFSP. It has a lot of logical strength. And I'm putting together a proof of this thing, and it's going in fits and starts. It turns out that I delayed the Ghent lectures quite a bit because I found out that unless it's done perfectly at the get-go, you have to rewrite it and change all the definitions, change all the setup. So it's just too delicate. It needs to be completely finished before one can give a lecture on it.
Harvey, how large?
This statement here is the SRP hierarchy, so-called subtle cardinal hierarchy. This is much bigger than weakly compact, much bigger than indescribables.
Okay,
But it's still compatible with V equals L.
okay,
For the much, much, much bigger cardinals, that's another talk.
okay.
There are things coming up there also, but not today. Okay, so
Okay.
this thing here is being done for real. Wish me luck that it completes well enough. But I have a stronger statement that's easier to reverse. But I'm a perfectionist. I want this one. Here's the stronger one that's easier to reverse. Every order invariant set has a maximal square whose less than I sections where I is less than n.
А там у него больше никого нет? Да.
Wait. Is that meant for me? Or is that an accidental voice?
It was unintended, I guess.
Okay. Every order invariant set has a maximal square whose less than I sections, I less than n, are order invariant over Z of In. In other words, it's the usual straddling thing. If you want to make the sections higher up, you're only going to get indiscernibles beyond there. That's an obvious generalization. That's easier to reverse. But I think that I can handle the other one as well. So I'm hoping everything is going to be fine. All right, now these statements are all pi 0, 1, although they don't look like pi 0, 1. They are pi 0, 1 because it's an undergraduate exercise to prove that every one of these statements merely asserts the existence of a countable model of a first order theory, of an effective first order theory. Every one of these things, you see, the maximal square is a model of a first order theory. Okay. And so all these statements are pi 0, 1, what I call implicitly pi 0, 1. Now there is a subject called explicitly pi 0, 1 that is even obviously more desirable. And that I deal with at the moment for the future, but the way I'm dealing with it is through finite games. I play, Alice and Bob sit there and play finite games. And it turns out that Bob wins, as usual, the males win. Bob wins, and that's a pi 0, 1 statement that's explicit. Okay, so we do that. And with a game approach, though, that is what I need to lever up to really big cardinals, such as the huge cardinal hierarchy. That's really, the huge cardinal hierarchy is far beyond what people get inner models with inner model, with determinacy in large cardinals. So that's where I'm headed, and I'm very grateful to Andreas for tolerating me canceling talks, because I have to have a real manuscript at hand, because otherwise I'll be talking nonsense. I'll have to change the talk I don't want a series of talks where each one changes the previous one. So I'm going to wait till I have this really done. I'm very excited about this. All right, I think I've finished.
Yeah, thank you very much. I think we can stop the recording.
Yeah.